Okay, students, 5.5, and today we're using trigonometric identities to help us with integration. So first things first, you're going to have a go. You know what your basic trig identities are, and I'd like to see if you could use those to answer any of these questions, and we'll be going through all of these as part of the lesson. So pause the video and see what you can do. Okay, and now I'm going to jump into going through a few questions, including these ones. And what we're going to do is kind of split them into more straightforward ones, where you just need to pick the right identity just based on what you're given, and then some slightly more challenging ones on the next page. So the identities that are most useful are these three, and these are going to come up in these examples here. So if I go into the first one, the integral of cos squared x, I can see which identity I'm going to use there, because I'm going to use cos of 2x. So cos of 2x is cos squared minus sine squared, but that's not the form we really want. The forms that we're going to be interested in these types of questions are the other two, so these ones. And remember, we get these just by substituting in like cos squared plus sine squared equals 1 to eliminate one of either the cos or the sine from this. But the point is that these can be rearranged to give us expressions for sine squared and cos squared in terms of cos of 2x. So sine squared is going to be 1 minus cos of 2x over 2, and cos squared is going to be 1 plus cos of 2x all over 2. And those are really helpful for integration. Depends obviously whether you've got sine squared or cos squared, which one you're going to use. We've got cos squared, so our integration here is going to become the integration of 1 plus cos 2x over 2 dx, which is the same as, take the half out of the front, the integral of 1 plus cos of 2x dx, which is going to be a half times x plus sine of 2x, but because the 2 would come out front when we differentiate it, it must be a half sine of 2x plus c. So that is a half x plus a quarter sine of 2x plus c. That's how we apply this identity to help us. With the second one, tan squared x, we don't know how to integrate tan squared, but fortunately, if we go back to our Pythagorean identity, sine squared x plus cos squared x equals 1, and then we do the transformation to take it to tan squared, so we divide everything by cos squared. That reminds us that tan squared of x is sec squared minus 1. So this is the integral of sec squared of x minus 1. And the good thing is we do know the integral of sec squared. We know that tan differentiates to sec squared, so sec squared integrates to tan. So this is just going to be tan x minus x plus c. And that's nice and simple. That's our answer. That's perhaps the easiest of the questions we'll look at today. And then the last one here, we can see this form, and this form is an absolute giveaway that we're going to use our double angle identity for sine. So sine 2x equals 2 sine x cos x, this one, because in the question that we're given here, we've got the integral of sine 2x cos 2x dx. Now here obviously I'm going to switch in 2x for x, and because I don't have the 2, I'm going to divide both sides by 2. This is going to give me the integral of a half sine of 4x dx. So doubling all these angles and then dividing by 2 will give me this integral, and sine over 4x I can definitely do, so that's a half times What differentiates to sine? Well, it's going to be minus cos of 4x, but if I differentiate this, I'm going to have to multiply by 4, so it's going to have a quarter in it as well. So overall, minus an eighth cos of 4x, and never forgetting the plus c. So, sorry, fell off the bottom of the screen there. Those are kind of 3 of the more basic type of questions. And then what we're going to do now, it shouldn't take us very long, is just look at 2 more interesting and slightly more involved questions. So, the way that we're going to split these out, and this is how you're going to decide what strategy to use, is we're going to look at 2 cases. We're going to look at the case where if we've got powers of sine multiplied by powers of cos, we're going to look at the first case where one of those powers is odd, and then we're going to look at the second case where both powers are even. And we're going to use slightly different strategies for each of those. So what I'm going to do is I'm going to talk you through the strategy, then I'm going to give you a chance to do it, and then we'll go through it. So what we're going to try and do here is we're going to try, where we've got an odd power, to use our identities to kind of get that power down to 1. So in this example here, we're going to get the sine cubed of x to reduce to sine x, and then everything else is going to be in terms of cos. And when we've got that, because sine is the derivative of cos, or it's very closely related to it, we can use substitution and the chain rule backwards. So if you have an odd power, we reduce the odd power to 1. How? By using Pythagoras, by using cos squared equals 1 minus sine squared. And then once we've simplified and got it to the power to 1, we use integration by substitution. Have a go at that using this example, and then when you're ready, I'll go through it. Okay, so I'm going to go through this question now. The way I'm going to split up the integral is to split the sine cubed into sine x times sine squared. This sine x is going to stick with me until the end, that's what I want. But what I'm going to do to the other sines is I'm going to get rid of those by swapping it for 1 minus cos squared. And then just to write this again, now I've got sine x times cos squared x minus cos to the power of 4x dx. Now, this form is when we can start to make a little bit of a breakthrough, because using our form for substitution, we have a function of cos times by the derivative of cos, which means that if we make the substitution with let u equal cos of x, so du by dx is minus sine of x, so dx is minus 1 over sine x du. Then this will help us deal with these. And we can also substitute in using cos x for these and these, meaning that all the x's can be replaced. So our integral I is going to be the integral of minus u squared minus u to the power 4 du. Because once I substitute in for the dx here, the sine x cancels with this sine x. I've still got the minus sign from here, but really this integral is just going to be, well, if we bring the minus sign in, it's going to be u to the power 5 minus, u to the power 4 minus u squared. So if I integrate that, it's going to be a fifth u to the power 5 minus a third u to the power 3 plus c. And then if I just substitute back in for u, my final answer is going to be 1/5 cos to the power 5x minus 1/3 cos to the power 3x plus c. And we're done. So I want you to just consider the power of this here. What we've done is you kind of carve off or chop off one of the signs from this odd power, and that's going to become your derivative when you do your substitution. Everything else, you change it to be the other trig. So because our derivative is sine, we have to switch everything else to be coses, and when we've done that, we can then use our substitution with u equals cos of x. This strategy we're always going to use when you have one odd power. Now, when they're both even, we need a completely different strategy, and the strategy when they're both even is you've got to get all the powers down to 1. And you're going to do that by using your formulae for cos and for sine. Cos of 2x and sine of 2x. So here is an example. We've got cos to the power 4 of x, and what we need to do is just keep using these identities until we get all the powers down to 1, and then you can integrate. I'd like you to have a go at it before I go through it. Pause the video and see if you can execute that strategy, and then I'll go through in a second. Okay, so I'm going to take you through it. So my integral here is obviously cos to the power of 4x dx, and I can remember from what I did earlier, well, cos squared of x is going to be cos of 2x minus 1 all over 2. That's my formula. So here I've got that squared. So the half squared is going to give me a quarter, and then it's going to be cos of, this is plus, isn't it? Cos of 2x plus 1 all squared dx. I'm going to expand that. I'm going to put my quarter at the front. That's going to give me cos squared of 2x plus 2 cos of 2x plus 1 of dx. And here I can see that I've definitely brought the power down. It's got smaller, but it's still not always 1. I've still got this cos squared. So what am I going to do here? I'm going to do exactly what I did before, and I'm going to substitute in using this formula. And here I'm going to have a half times cos of 4x, because I'm doubling the angle. I'm using this formula again, but this time with 2x and 4x, plus 1. Then I've got these two other terms, plus 2 cos of 2x plus 1 dx. In other words, I've got a quarter times the integral of a half cos 4x plus 2 cos of 2x, and then my constant term I have plus a half and plus 1, so I have plus 3 over 2. I integrate all of this with respect to x. So what have we got? A quarter times an 1/8 sine of 4x. Then from this one, the 2 is actually correct, so this is just going to be sine of 2x, and this last term here, just 3 over 2x plus c. So just expanding, 1 over 32 sine of 4x plus 1/4 sine of 2x plus 3 over 8, using the coefficient at the front, x plus c, and that's our final answer. So just to recap, when both m and n are even, the same powers, we can use these identities to reduce all the powers to 1. The disadvantage of those kind of questions is quite often that involves this kind of expansion, like we ended up with a quadratic in the middle, which meant you just get more terms, and you will see some questions which have more terms than this, where it gets more complicated. But if you can get everything down so it's a power of 1, then you know how to integrate cos of kx or sine of kx, and so you can answer it. Good luck with the exercise today. As normal, let me know which questions you struggled with, and then we can go through those at a later time. All the best.